Assalamu alaikum, I'm Maybe Shihab and I'll be presenting the Group Night Final Assignment Elevator Controller System. Our group members are Ayham Alvi, Maybe Shihab, Pritam Roy and Mohammad Mahian Islam. So, for the overview, this project focuses on the design and implementation of a synchronous digital counter and display control system using fundamental logic components. The circuit integrates flip-flops, logic gates, counters, multiplexers, LEDs, and 7-segment light displays to demonstrate how sequential and combinational logic can be combined to build a complete digital system. The system processes clock pulses and controls inputs to generate a continuing sequence which is then decoded and displayed in a human-readable numerical format. Problem statement: the previous elevator controller design is insufficient to support an 8-floor hotel elevator system and lacks essential control features. To overcome these limitations, the system must be enhanced to implement a 3-bit synchronous up-down counter capable of representing all the 8 floors. This also requires Carnot map signification and input control integration. For solutions to these problems, a 3-bit synchronous up-down counter is designed to support an 8-floor hotel elevator system. The counter is implemented using JK flip-flops, all driven by a common clock signal to ensure synchronous operation. The counting direction is called by an external input "x", as signified in the group registration form, where x is 1 the counter counts up, and when x is 0 the counter counts down. The present state and next state behavior of the counter is analyzed using state tables and the required JK flip-flop excitation values are obtained accordingly. To derive simplified logic expressions, 4-variable Carnot maps are constructed using the inputs x, q2, q1, and q0. These K-maps are used to design the combinational logic, deriving the j and k inputs of each flip-flop. In addition to floor counting, the input controller is enhanced with extra safety and access features. This includes visitor card detection, door open or close indication, and passcode verification. Logical conditions are applied to ensure that the elevator operates only when all valid input requirements are satisfied. We implemented a two-part solution: Part one: input validation secure access; Part two: floor counting with a 3-bit synchronous up-down counter using JK flip-flops, Carnot maps, and display logic. As for the system implementation, the system was implemented and simulated using DEET software. The Figure 1 Part A is the simplified system and the Part B is the enhanced version. Circuit description. Circuit description. The circuit consists of the following major sections: power and clock section provides logic, high and G&A references, generates a clock signal used by all sequential elements. Flip-flop section. Multiple flip-flops store the system state output are fed into logic gate and counters. Logic gate network processes flip-flop outputs, generates, enable, reset, and control signals. Counter section receives clock pulses, produces binary count values, operates synchronously with the flip-flops. Display section binary outputs are decoded. 7-segment displays present numerical values. While making this project, our working principles were: when power is applied, the circuit initializes to a known state. On each clock pulse, flip-flops update their stored values. Logic gates evaluate conditions based on the current state. The counter increments or resets accordingly. The resulting binary output is decoded. The decoded value is displayed on the 7-segment display. This cycle repeats continuously with each clock pulse. The synchronous nature of this design ensures predictable and stable behavior. Now we have come to our conclusion. This project successfully demonstrates the design of a complete digital system using sequential and combinational logic by integrating flip-flops, counters, and display units. This circuit showcases how theoretical concepts translate into functional hardwares. From this project we learned importance of clock synchronization, proper use of flip-flops for state storage, practical decoding of binary values, debugging complex logical circuits, and many more things. That's all from Group 9. Thank you.